So if a system absorbs heat, absorbs thermal energy, then the temperature increases. And we call the temperature change delta T. It's the final minus the initial. The change in temperature is proportional to how much heat was absorbed. You put more heat in, the temperature changes more. The proportionality constant is called heat capacity, C. And the units of that are joules per degree Celsius or joules per Kelvin. So you put more heat in, you get a bigger change. So we can see that the heat is let's had a brain fart. The heat equals the heat capacity times the change in temperature. And so the units work out there. The heat capacity would be in, say, joules per degree Celsius, and the change in temperature would be in degrees Celsius, and so those would cancel out, and we'd end up with a unit of joule, which is an energy unit. What is heat capacity? It's the amount of heat required to change the temperature of the system by 1 degree Celsius. So that's going to depend on what the system is, right? If the system is bigger or smaller or different substances, that's going to change. So the heat capacity of an object depends on how much of it there is. That makes it an extensive property. Extensive properties are important, but they're not always very useful because they keep changing. You know, the mass of something, it depends on which sample you're talking about. Things like density stay the same. Those are intrinsic or intensive properties. So we can make the heat capacity into an intensive property by taking into account the amount of matter. So specific heat capacity, your book symbolizes this as C sub S. That's the intrinsic capacity of a substance to absorb heat. So it depends on the amount of stuff, but it also depends on the material. So specific heat capacity is the amount of heat needed to raise the temperature of 1 gram by 1 degree Celsius. So now we've included an amount here. So this is going to have units not of joules per degree Celsius, but joules per gram degree Celsius. Sometimes we refer to a molar heat capacity, and that's the heat needed to raise the temperature of 1 mole by 1 degree. So this is a very useful and important equation. You need to memorize this. Q equals mc delta T. This is the specific heat capacity. We'll actually find that we rarely use heat capacity. So sometimes I'll forget the S on there, but we're talking about specific heat capacities here. So the heat, Q, in joules is equal to the mass of the substance in grams times its specific heat capacity in joules per gram degree Celsius times the change in temperature. So the change in temperature, delta T, is always T final minus T initial. This is a table from your textbook giving specific heat capacities of some common substances. And the units are given up here, joules per gram degree Celsius. So here's water. It has a specific heat capacity of 4.18. The metals here have much lower specific heat capacities. That's an F. Let me clean that up a little bit. That better? Final minus initial. Don't memorize these. I'll give them to you on an exam. If you're doing homework or a lab, you just go look them up. So water has a very high specific heat capacity. It was 4.184. Everything else there was much less. That means that water can absorb a lot of energy without changing its temperature very much. And this has a huge influence on our climate. So here's a picture of the Golden Gate Bridge in San Francisco. There's a lot of water surrounding the peninsula, this San Francisco peninsula there. The temperature, I used to live there. Don't ask me why we moved to the Fresno area, but I used to live there and the weather was awesome. It hardly ever changes. You know, it would be maybe 70 in the summer and 65 in the winter. And it didn't change much through the course of the day. Here, we might have a day in the winter where it's, 40 degrees as the high, and in the summer it might be 115. And on that day when it's 115, it might get down to 65 or 70 degrees that night. 40, 50 degree temperature changes. I mean, the temperature just goes up and down like crazy around here. That's why no matter how you dress, at some point of the day, you're going to be hot, and at another part, you're going to be cold. It's just a fact of life. And some people, I think, just choose to completely ignore temperature, and they just wear what they like, and they just, I'm hot, I'll be cold later, it'll be fine, right? It's the water surrounding the San Francisco Peninsula that moderates the temperature. The sun beats down during the day, and that radiant energy heats things up. The water only goes up a little bit in temperature. At night, when the sun goes down and we don't have that radiant energy coming in, the air gets cooler and the water releases energy back into the air, and so it keeps the temperature from fluctuating very much. We use water as a coolant because it can absorb a lot of heat without getting too hot. So that's why we use water in the radiator to pull heat away from important parts of your engine. Okay, so we're going to do a lot of calculations with that Q equals MC delta T. So here's a problem. Lots of words. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. It'd be a lot easier to do the density, but then it wouldn't work for this part of the lecture. She first weighs the rock and finds it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 to 47 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. Like density, specific heat capacity is an intensive property. It doesn't change. It's always the same. So gold always has the same specific heat capacity. Well, how do we calculate this? We need an equation. And the equation is Q equals MC, that's C sub S, delta T. So they're asking us to find the specific heat capacity. That's the C. So we just need to rearrange. We'll divide by M, divide by delta T on this side. Do the same thing on that side. So we've got the specific heat capacity. It's going to be equal to Q divided by M and delta T. Now we know what we're looking for. Let's look for these variables, these quantities. Q is heat. Okay, it absorbs 57.2 joules of heat. So Q equals 57.2 joules. Q can be positive or negative. You can gain heat or you can lose heat. Is this positive or negative? It's positive. Because here the rock is the system. The rock is gaining energy, it's positive. And the mass is given to us, 4.7 grams. And then we need the change in temperature. Delta T, that's going to be the final temperature minus the initial temperature. It's important that you get those straight because that'll change whether delta T is negative or positive. Mass is always positive. Q can be negative, delta T can be negative. It just means that the temperature went down instead of up. So final temperature, it says 25 to 47. So it went to 47 from 25, and so we subtract And we get what, 22. That's our change in temperature. So now we can stick everything into our equation. We've got 57.2 joules divided by the mass, 4.7 grams, and the change in temperature, 22 degrees Celsius. So 57.2 divided by 4.7 divided by 22. How many sig figs should this have? 2. So I'm going to write down 0.55, and I'm going to put 2 more. What are the units? Joules over grams and degrees Celsius. Nothing cancels out. It's okay. I know we haven't seen that happen a lot yet, but it's okay. So joules per gram degrees Celsius. Those are the units of specific heat capacity, so we should be okay with that. So here is the specific heat capacity of the rock. How do we find out if it's gold? We have to compare it to the known specific heat capacity of gold, which is 0.128. Is it gold? Nope, just a pretty rock. Any questions? So when you have two objects at different temperatures and they are in contact with each other, the heat will flow from the higher temperature to the lower temperature, and they're going to go to the same final temperature. I know I already said that, but it's a point that sometimes gets overlooked. So we can do experiments like this, and we're going to do one, I don't remember exactly when, but it's on the schedule. So here we have a beaker of water. The water was at 25 degrees Celsius, and we take this block of metal at 55 degrees Celsius and we stick it in there. Hot metal in room temperature water, what's going to happen? Water heats up, metal cools down until they get to the same temperature, which will be lower than what the metal started at and higher than what the water started at. So we've got this thermal energy transfer. The amount of energy lost by the metal is equal to the amount of energy gained. So the numbers are the same, the sign is opposite. Which one's negative and which one's positive depends on which one you're calling the system. If you're looking at the metal as the system, then it's negative. If you're looking at water as the system, it's positive. And so don't worry about where the negative sign is. One has the negative sign, the other one doesn't. Because if you want it, you can switch it to the other side. They're just opposite. So if Q metal is equal to the opposite of Q water, we know that Q metal is equal to the mass of the metal times the specific heat capacity of the metal times the change in temperature for the metal. That must be equal to MC and delta T for the water, but change the sign. And so this is how we can measure the transfer of energy, because we can stick a thermometer in here and we can see what the final temperature is. Any questions? Okay, so a block of copper of unknown mass has an initial temperature of 64.5 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? We'll ignore the fact that there's a much easier way to find the mass of the copper block. Stick it in a balance. So there's my beaker, and we have water. Does that look blue? That is blue. And we've got a piece of copper. So there's my copper. it's important to sift out these numbers and assign them their proper variables. So let's think about the copper first. What do we know about the copper? We don't know what the mass of the copper is. We know the mass of the water. Do we know the initial temperature of the copper? Yeah, that's 65.4 degrees Celsius. Do we know the final temperature? Yeah. So the final temperature is 24.2 degrees Celsius. Do they give us any other information about the copper there? No, they don't. Okay, so let's see what we know about the water. Do we have an initial temperature for the water? Yes. 22.7 degrees Celsius. What's the final temperature of the water? It's 24.2. It's the same. Because the heat transfer occurs until the temperature is the same. Do we know the mass of the water? Yeah, that's the 95.7 grams. Okay, so that's all the numbers that they gave us. Well, we could calculate delta T, right? We could do that. Delta T for the water is the final minus the initial. So 24.2 minus 22.7. I think that's 1.5. We can calculate the change in temperature for the copper. That would be the final. I'm not going to write this out. The final is 24.2, and subtract the initial 65.4, negative 41.2 degrees Celsius. The negative is important. That means the temperature went down. So we've got heat transfer occurring here. We've got here what we're doing is we're going to define the copper block as the system, and we're going to call the water the surroundings. The water is what's in contact with the metal. We're not going to worry about the person who's standing over here watching. They're not going to really get any heat from this block. The water's going to get all of it, essentially. So Q for the metal has to equal what? Negative Q for the water. Heat lost by the copper is equal to the heat gained by the water, but the sign is opposite. And then we can look at this and say, well, what is Q? Q is mc delta T. So this is the mass of the water times the specific heat capacity of the water times the change in temperature of the water, with a negative in front, because it's opposite. And then on the other side, we've got the mass of the copper times the specific heat capacity of the copper times the change in temperature of the copper. Well, we've got the mass of the water, we've got the change in temperature for both of them. We're missing specific heat capacities. We have to go look them up. So I remember the one for water. So the specific heat capacity for water is 4.184 joules per gram degrees Celsius. I almost remember the one for copper, but I'm not going to trust that memory. Over here, copper, 0.385 joules per gram degree Celsius. I'm going to stick it up here. I ran out of room. 0.385 joules per gram degrees Celsius. So the only thing we don't know is M for the metal, the copper. Well, that's cool. So what I want to do is I want to take this equation and rearrange it and then stick numbers in. That's usually the safest thing. So I'm going to divide by CS on both sides. See, I need a line. I'm going to divide by CS. And on the other side, it's going to cancel out. And I'm going to divide by delta T for the copper. And so it's going to cancel out on the other side. And then let's just move that guy over. So the mass of the copper equals minus the mass of the water times the specific heat capacity of the water times the change in temperature of the water divided by the quantity, specific heat capacity of the copper times the change in temperature of the copper. Lots of letters, lots of numbers. Write it out clearly and you'll be fine. Okay. If you're not using multiple colors, which normally you would not do writing on paper, then you're going to use subscripts. So you're going to, let's see, think, oh, where'd it go? I'm going to get lost here. There, like this, Q metal, Q water. So I'm just going to plug all these numbers in. I'm just going to use one color because I'm getting tired of switching back and forth. So the mass that we're looking for equals, don't lose that negative sign. So I'm going to put in the mass of the water, 95.7 grams. Specific heat capacity of the water, 4.184. That's not a very good 4 joules per gram degrees Celsius. Times the change in temperature, 1.5. All of that divided by the specific heat capacity of the copper, 0.385 joules per gram degrees Celsius, and the change in temperature of the copper, which is minus 41.2 degrees Celsius. Units work out. I've got joules per gram degrees Celsius up here and down here, so I can cancel those out. I've got degrees Celsius and degrees Celsius, those cancel out. And I'm left with gram, a unit of mass, which is awesome because I'm trying to find a mass. So I've got negative 95.7 times 4.184 times 1.5 divided by 0.385 divided by negative 41.2. My mass equals, how many sig figs should this have? 2, because of that 1.5. So 37.86 grams, which we would round to 38 grams. Hiding down there at the bottom. Any questions? These problems are more tedious than anything else. And you've got mass and specific heat capacity and change in temperature for 2 different things, and so you just need to keep them straight. Yes?
On the exam, are you going to provide the specific heat capacity?
Yeah. The specific heat capacities would be given unless they're asking you to calculate it based on the data. Yeah, you don't need to memorize those. Any other questions? So we talked a bit about Q, about heat. We're going to talk about work. Really the only kind of work we're going to deal with in Chem 1A is what's called pressure volume work. This is work caused by a volume change against an external pressure. So this is the sort of thing that happens in your car engine. So here in the cylinder, you have combustion of the gas-air mixture. It explodes, it exerts pressure against the piston, which causes the piston to move. So there's a change in volume, and it's against an external pressure. That's work. And that causes I'm blanking on all the names, so it just eventually causes your wheels to move and you go forward, which is good. When gases expand, delta V is positive, but the system is doing work on the surroundings, and we define that as negative. So in this equation, the pressure volume work is equal to pressure times the change in volume, but we need a negative in there. Pressures can't be negative, and when something does work against the surroundings, it expands in volume, which is always positive, so we need the negative in there. Here's another look at it more close up. So the initial state is here. It expands, it increases in volume, and causes the piston to move. So it's doing work. So here is a useful conversion factor. You don't need to memorize that one either, but you need to know that it exists so that you can go look for it, because it's not super obvious. Joule is a unit of energy. That makes sense. Atmospheres times liters is also a unit of energy. So 1 atmosphere a liter is equal to 101.3 joules. Another problem. A cylinder equipped with a piston expands against an external pressure of 1.58 atmospheres. If the initial volume is 0.485 liters and the final volume is 1.245 liters, how much work in joules is done? So they're asking us about work, right? How much work is done? Well, the only equation we have for work is negative the pressure times the change in the volume. Well, do we know what the pressure is? Yeah, it says it's 1.58 atmospheres. The change in volume, that's the final volume minus the initial volume. So the final volume is 1.245 liters. The initial volume is 0.485 liters. 1.245 minus 0.485. My calculator gives me 0.76 liters. What's wrong with that? Starts with an S. Something. 2 words, starts with S and F. Sig figs. We're subtracting here. The rule for subtraction is you look at the number of decimal places. Both of these numbers have 3 decimal places, so the answer should have 3 decimal places. So I need to put a 0 in there. This number has 3 sig figs. Okay, so now I've got P and I've got V, delta V, so I can put them in here. Negative 1.58 atmospheres times 0.760 liters. I come up with 1.2008. That would have 3 sig figs. What are the units?
Atmosphere liters?
Atmosphere liters. What's the? It is negative, thank you. I was testing you. Negative. Atmosphere liters. What does the question ask for? Joules. We have to convert. I'm going to do this down at the bottom. So negative 1.2008 atmosphere liters. I need a conversion factor 101.3 joules is equal to 1 atmosphere liter. So 101.3 joules is equal to 1 atmosphere liter. And this should have 3 sig figs. So now I've got my units, and I'll sum it around this. Minus 122 joules. Now these negative signs, I know this is confusing and I'm sorry. I'm just going to try to explain how to think about these. How much work is done? It's like, okay, how much money did you give Tommy? Am I going to say negative $2? No. I gave him 2. The word gave indicates the direction. So when we report this answer, 122 joules of work was done. So as you're answering questions in Mastering Chemistry, it may seem like those negative signs just kind of come and go randomly. Like, why do I need the negative now and not this other time? It's very confusing, I'm sorry. But it's the words. If the words are indicating the direction, then we don't put in the negative sign. Just like with money, right? You know, I bought those baseball shoes. How much were they? Negative $85. Well, that kind of implies that someone paid me to take the baseball cleats, right? But no, I paid $85. If you say, well, what's the net difference in your account? It's negative 85, okay? So if you're confused about things like that, transfer it into a money situation, and it'll make a lot more sense. Any questions?